So I would like to go into this I transformation next, if there are no questions about this. Okay. And remember, all of this is being applied to these points. So if I have a, you know, x, y, z 1 here, right, x, y, z is the point that I want to apply. That's like a point on this cube that I drew, the yellow cube that was drawn in the previous figure that I made on the board. I just put the point here, add a 1 to it, apply all of these transformations, and then I will figure out in some kind of pixel coordinates that look like floating point numbers or real numbers, depending on whether you're using a computer or not. It will give you these coordinates that are not necessarily integers. All right. So I want to figure out the I transformation. And to make it really clear, I will call it Cyclopean I transformation. So if you're trying to imagine, maybe people do not make a distinction in computer graphics about this, but if you're doing virtual reality, then you could build a virtual reality headset for a Cyclops, and then this would be just fine, right? But because you have two eyes, I don't want to pick the right or the left. I'd rather pick the midpoint between them to make everything simple here, and then talk about how to do a nice offset for left and right. So that's why we'll imagine that we're designing a virtual reality headset for a Cyclops in the beginning here. All right. So the first thing to do is to imagine that, let's see, to express the eyes rotation and translation in the world. So in other words, I just imagine that this eye, it's like an eyeball with a pupil, is defined in some kind of body frame. Let me give you what's essentially the body frame of the eye. I want to put the pupil right at the origin, because that's the point where the light comes in the real world. So this is all virtual that I'm drawing here, but nevertheless. Y, I have z running into the eye, and the only reason why we're doing that is so that we can maintain right-handed coordinate systems. So it's another one of these annoyances that it's here for a good reason, because if you don't do it this way, then you'll have more annoyances. So it's a trade-off. And remember, x is out. So this is essentially a body frame for the eyeball. And now if I take the eyeball and place it into the world, there's going to be a transformation for that. That's going to be a rotation and a translation of the eyeball. I want to figure out what that transformation is based on how I place the eyeball, and then I want to use that to make the eye transform. So one way to do that, which is very common, is to consider what is called a look at. Look at. Somewhat strange name, but a look at. So here's how this works. We have three things. We have position of the eye. Sometimes I'll say position, sometimes I'll say translation, sometimes I'll say orientation, sometimes I'll say rotation. So rotation and translation are the operations, and then the result is orientation and position, correct? So it's okay to interchange those as long as you understand what's going on. So 2, I want to have a looking direction and 3, I need to specify an up direction. So let me give some notation to these, and I will explain it. So the position of the eye I will just use as a vector E. So I'll just write it as E like this, single letter. And then the looking direction will be C. Get a little hard to write here. I'll put a hat on it to denote that we have unit vectors. And U, put a hat on to note it's a unit vector. If you don't like my hats, leave them off, but they're unit vectors, so I'm trying to denote it somehow. All right. So how can I obtain the look at? Here's one possible way to do it. So I have the eye, and I've determined that I've decided that the pupil is going to be located at some location E, so it's very easy to write down. So imagine you're given where the eye is. It'll have some coordinates that correspond to where the pupil is at. I will call that E. And then if you are told that, let's see, if you're told that the pupil is looking at a particular point, let's see here, get rid of that. So the eye is pointed towards a particular point here, call it L, then you get a vector, let's say a vector that corresponds to traveling from the pupil to the point L. So I can just call this vector C. I'll say that C is, just using the simple coordinates that you have here, the Cartesian coordinates of the world, L minus E. Right, so that gives me that vector. Right, so that gives me that vector. And then my C hat, which is the looking direction here, number 2, and I've given you number 1 by just simple specification. Number 2, I just normalize that vector. So L minus E divided by the length of that vector, L minus E. Correct? So that's, what am I doing? I'm trying to specify the coordinate frame that I get here, right? How is it oriented in the world when the eye is looking at a particular place? So I just want to describe that. I want to figure out that coordinate frame, and then from that very easily construct a rotation matrix that will put the eye in that orientation, and of course construct a full homogeneous transformation matrix that will also put it in the right location. But that part is considerably easier because it's just translation by E. So I need to figure out the orientation of this eye. I'm trying to put together the coordinate system. It looks like once I figured out C hat, I should essentially have the Z part, right? It's just pointing in the wrong direction, so it'll be the C hat corresponds to minus Z. And then there's also a possible role with respect to that has to do with the up direction, which we will have to take care of. And once we have the up direction and we have, let's say, the forward backwards direction, we can do a simple cross product, right-handed cross product, to determine the third axis, the third direction. And we've agreed to do right-handed coordinates, and so that will matter. So if that's the case, then if I want to figure out these axes, so the let's say coordinate axes for the eye in the world, then I get x hat, y hat, z hat for these. And as I said, z hat is going to be minus c hat. So I'm figuring out that one. If I have this eyeball oriented somewhere, I'm figuring out that part. And then x hat I take the up direction and I cross it with z hat. Right? So I take my up direction, I cross it with z hat. And I guess y should y just be u hat? Does that make natural sense? So when I started teaching this, I thought y should be u hat, and then I noticed it wasn't in the textbook, for example, by Shirley that we're using, and it's not in a lot of the graphics literature, and it is instead just z cross x, right, z hat cross x hat, which is also fine. The reason why they do not use u here directly is just in case someone gave you a u that was not perfectly parallel to the image plane, right? So it doesn't correspond perfectly. It's not. So if I look, if the eye is actually my eye, then if u instead of pointing straight up is slanted some, this would correct for that if you do it in this way. So it will tolerate a sloppily defined up if you want. So yes. These are all in the world frame, correct? Yeah. I'm trying to imagine that the eye has been placed into the world frame, and I'm working with a description of that. Somebody tells me, well, the pupil is at this location and it's looking at this particular point. In other words, that point should be in the center of its image, right? That's the point L here. That would be in the center of the image. From that, I make this vector C by just subtracting these 2 points, and then I get the look at direction essentially, right? Like what way are you looking? And then the only thing that matters is, you know, is the camera upside down, right side up, how exactly is it oriented? That's the next part that we're trying to figure out, which is handled by this last step. I am taking the up into account here, and I just keep performing Cartesian products to get everything, to get my coordinate frame orthogonal and right-handed, regardless of whether somebody gave me a sloppy u value that is not perfectly orthogonal to my other axes. So it allows you to be sloppy with u. Personally, I would say get it right the first time. Don't be sloppy about it, but this will fix a little bit of slop in that. So once I have that, I get now a rotation matrix, Ri, where, let me just write it out with dots, and then these columns. This column is just x hat, this column is y hat, and this column is z hat. So this gives me a rotation matrix. Do we agree with that now? This gives me a rotation matrix that if I start off with my eye defined in its body frame and I apply this rotation matrix to it that I've constructed, it should, it doesn't translate the eye, but it should rotate the eye so that it's looking in the right direction. Do you believe that? Is that okay? So that's what we have. If I want to also translate it, then I would, after performing the rotation, I add E, the x, y, and z components to the result. I can do it all together in one homogeneous transform. Does this solve our problem of trying to figure out what the perspective of the world is from the eye, from the eye's coordinate frame? I think I did it backwards, didn't I? I figured out from the coordinate frame of the world how the eye appears. I need to do in the other direction. How do I solve that? All right, so let's see. If I'm, you know, I'm standing here, I turn my, we've talked about this before, I turn my head, let's say counterclockwise 45 degrees. How does the world appear to have moved from the reference point of my eye? If I hold my eye still, it appears that the world has rotated in the opposite direction, right? It's an inverse transform. So that's what we actually have to apply. We don't want our eye, we want the inverse. And we don't want the translation E, we want the inverse. And so the way to imagine it is as if your eyeball is being held fixed and it's the world that's moving around all the time, quite wildly, I guess, because if I turn my head quickly, it would take a lot of energy to move the world around that fast, right? So it's a bad relativity problem, right? But that's how the mathematics feels like when you perform these transformations. So the eye is being held fixed all the time because the screen is being held fixed relative to the eye, and you're going to be presenting images to that ultimately. So this is being held fixed and the world is being transformed. So we need the inverse. Now remember, I just gave you a warning about taking the inverse of one of these transformation matrices. So let me give you the inverse now, and then we'll stop and take a break, which I seem to have forgotten to do. I got a little too excited, so let's see. So let's give you the final result. So Ti is equal to I need to have as the columns x hat, y hat, and z hat. Sorry, I need to have as the rows. I said columns was wrong. I need to have as the rows x hat, y hat, z hat, because I'm performing the inverse transform. Also, I need to extend this because I'm not just going to apply rotation here. I'm going to put it together in homogeneous form. So this is just the rotation part. This corresponds to that Ri there, transpose, which, because it's a rotation matrix, this corresponds to Ri inverse. And then I have the remaining components. And I make this. So that undoes the rotation. And then I have the undoing the translation part, which should have my negative e coordinates here, negative ex, negative ey, and negative ez. Right. So, I've inverted the placement of the I. I undo the translation, which is this matrix here. It's on the right, so it gets applied first, and then I undo the rotation, which is the transpose of the rotation matrix that we built using the lookat. You don't have to build it from a lookat. You may get it directly from a filtering algorithm that's doing head tracking, right. So, it may come from another place, but traditionally in graphics it comes from a lookat, so I wanted to build it from that as well. But it may just come directly from the tracking, and it may come from some combination of the two as you move a controller around. So, it'll come from different sources. It's not a constant, but once it's given and fixed, this is how you obtain T sub I. Questions about that? How do you find?
How do you find the rotation matrix?
Oh, I think I just did it. So I mean, I basically, if you remember when I was covering 3D rotations, in fact, when I went all the way back to 2D rotations, I was trying to convince you that the columns correspond to how the coordinate axes get rotated. Right. I did that in the 2D example, and the 3D example was the same way. That's why we had these constraints. Remember when I was saying the columns have to be orthogonal, so they have to have an inner product of 0, and they have to have length 1. So these are how the coordinate axes are transformed by the rotation. So I figured out what these are by the geometry of the lookat, and then I just write these directly into the matrix, and that automatically forms the rotation. So it's a very good question, and it's a very easy thing to forget. But whenever you look at a rotation matrix, remember that the columns are these are the coordinate axes normalized and showing exactly the effect of this rotation matrix on the standard basis elements. So if you take the x, y, z basis elements that are 0, 0, 1, 0, 1, 0, and sorry, I should start, I could go right in order. If you take the basic coordinate axes 1, 0, 0, 0, 1, 0, and 0, 0, 1, transform to 3 of those with this rotation matrix, you'll get exactly the expressions in these columns. So it's just a direct step. Long answer for a short question. Hopefully it's clear.